In the previous episode, I showed you how to create a custom Linux distribution for the STM32MP1 using the Yocto project. We have the output image files ready to go, so let's flash them to an SD card and see if we can boot into Linux. At this point, we should have a number of image files ready to be burned or flashed onto an SD card. I'm going to open up a file explorer so you can see what's going on rather than using the console for this. If we go to our projects directory, go into Yocto, go to our build directory. Here you should find a temp folder, go into that. In here you should see deploy, and then images. The folder in here might be named differently if you are using a different vendor, but for the STM32MP1 series, that should be the name of the folder. In that folder there are a bunch of files. Ideally, you should have something like sdcard.image like we saw in the build root episode that you can just flash an entire SD card with, but we don't have that. So what we're going to need to do is construct the correct partitions for our SD card and then flash the necessary files from within here onto those partitions. This is where things can start to differ among the vendors. So at this point, you definitely want to read the vendor documentation about the specific boot sequence for your particular platform. In this case, ST has this great presentation about how the MP1 platform boots. If we look through this, you can see the stages of the bootloader. Interestingly enough, Linux often does not just boot from nothing. There is a series of stages that it has to go through in order for the kernel to start running. And that's because of the limited RAM and oftentimes ROM or flash space available on the chip itself. Since the chip, the microprocessor, doesn't know about external RAM, you need a bootloader to tell it where to find that and other peripherals that might be needed in order to launch the kernel, such as where is the root file system located. ST gives a great analogy of this, comparing the boot chain to something like launching a rocket with multiple stages. When you first power on the microprocessor, there is hard-coded ROM code in that microprocessor that will run. It configures basic clocks and then looks for the first stage bootloader. For the STM32MP1, it does so by looking at the configuration of a few pins, which on our dev board is those switches, and those should both be set to on in order to tell this ROM code to look at the SD card for the first stage bootloader. That first stage bootloader finishes initializing all of the clocks, sets up the external RAM, and looks for the second stage bootloader. The second stage bootloader is something like U-boot or Grub or something that you might be familiar with. This is the thing that actually launches the Linux kernel. And it's also used to set up things like Ethernet, find out where the root file system is, and it looks for other devices in device tree blobs, these .dtb files. Once the second stage bootloader is finished setting up everything, it launches the Linux kernel, mounts the root file system, and then you should be given access to the Linux user space, and that's the console that you're used to. We're going to have to set all of this up manually, but lucky for us, we have images for things like the first stage bootloader, second stage bootloader, the Linux kernel, and the root file system that we can just flash onto an SD card. Further down in this documentation, you can see the recommended flash partitions for something like an SD card. The first stage bootloader should take up no more than 256 kilobytes. It's also saying maybe 512, but I found that 256 kilobytes seems to work just fine. The one thing that this diagram is not showing you is that you need to have 2 copies of the first stage bootloader in case one of them fails or gets corrupted. So you should really make 2 different partitions, each that are 256 kilobytes. The next thing is the second stage bootloader. This is another image file, usually something like U-boot and various device tree blobs, or in this case, 1 device tree blob, and this partition should be 2 megabytes. It also looks for a boot file system that contains various files to help during the booting stage. This can be things like the Linux kernel device tree, the U-boot image itself. and the distro configurations in the extlinux.conf file, which we will have to modify in order to mount root file system correctly before it boots into the Linux kernel. It also recommends having a vendor file system. This contains things like third-party binaries for things like networking drivers, if they're proprietary, or graphics card drivers. We won't need this for this particular demonstration, so we won't have to mount vendor FS. Another thing you'll often see in a lot of Linux distributions is a separate user file system such that users cannot modify the root file system. This is actually a very good security practice, but for our purposes, we're not going to mount this either. We're just going to work in root file system and do everything as root for now. Note that if you want to set up good security, only have one user or no user at all, you may want to have a separate user file system that gets mounted that anybody who logs in cannot modify the root file system and they have their own little sandbox to play in. However, we won't be covering generic Linux security practices. That would be a separate course, so I recommend learning more about how to secure Linux when it comes to deploying your embedded Linux device. In early versions of ST's board support package, they supported this U-boot secondary program loader to act as a first stage bootloader. However, that has been since deprecated. Even though you can find images of it in the output directory, it will not work for us. As a result, we have to use this ARM Trusted Firmware, or TFA, as our first stage bootloader. If you keep reading through this, you will see that ST requires us to use the GUID partition table GPT format instead of something like the DOS or master boot record, which can change how we format our SD card, as many SD cards come pre-formatted with MBR instead of GPT, so keep that in mind. We will have to remember that when we're flashing our card. This presentation only gives a basic example of how things need to be set up for the SD card, and we don't need to worry about these T partitions here. We just care about the first stage bootloader 1 and 2. Those are the two copies. The second stage bootloader, our boot file system, because that's read by the second stage bootloader, and the root file system. Those are the only things we care about just to get something basic working. So let's go back to our host machine, and ignoring many of these files, we can look at something like the flash layout core image minimal. And in here, there is no basic boot chain that we can use, so we go to trusted. These give you scripts for how the SD card will be partitioned and what images will be copied to them. We'll find the script for the SD card and our board, which is the 157D-DK1. Let's open that up in a basic text editor. ST really wants you to use their proprietary tools for flashing an SD card for their chips or their boards. And these scripts are read in by that proprietary tool in order to do that. But we're going to avoid using that tool for now and set up a card manually so you can see how that process is done and start to get an idea of how a boot chain works and how to set up a boot chain. These first two lines don't tell us a whole lot. Since we're looking at these partitions over here, we care about the first stage bootloader 1 and 2. We will try to keep these partition names to be exactly like this, so we're going to use FSBL1, FSBL2 for the two copies of the first stage bootloader. The image that's being flashed to these partitions can be found in the ARM Trusted Firmware folder, and it's the TFA, the name of our board, -sdcard.stm32, so I'm just going to trust that this is an image, and since I've already tested this, yes, this is an image that we can just flash using DD directly to this partition. The second stage bootloader is this FIP file, or rather this firmware image package. It's a container that ARM uses for loading trusted firmware into the boot process. And for our board, we need to go into FIP. We'll find the FIP-board name-trusted.bin. This is an image file for our second stage bootloader. And it will look for the boot file system, which I call mine bootfs, but boot probably also works. This is going to be in that top level directory where the images are created, and it's going to be the stimage-bootfs, Pokey from the reference distribution, and the name of the processor.ext4, which is just a partition that we can copy directly in. We're going to ignore vendorfs and rootfs since neither of those are required to get our board to boot. Instead, we do care about root file system, and that is the core image minimal stm32mp1.ext4. So this tells you where to find the particular images that we're going to use to flash to our SD card partitions. Knowing that, let's head over to our console. Plug in the SD card into your host computer. If you're running some flavor of Debian, you'll probably have the partitions auto mount. You can see that I have a previous set of partitions already set up on this SD card. You will definitely want to unmount those. I will use the GUI method of unmounting these, which is just clicking this eject or unmount button. That should unmount both of those partitions. You're welcome to use the console umount command if you wish. But now we just have a raw SD card plugged in. We can see the partitions, but they're not mounted in our file system. I recommend using the list block or lsblk to view the partitions and what's available. You can see I've got a bunch of things acting as hard drives on my computer here. What we really care about is this mmcblk2 block. This is an 8 GB card and it has 5 partitions on it already. We're going to want to delete any of the partitions that we have available. If you're coming from the build root episode, this will probably be 2 or 3 partitions. Either way, you want to wipe all of those clean. To do that, we're going to use fdisk. You'll want administrative privileges, so call this with sudo, and then tell it where the raw device is. So in this case, my SD card is mounted on /dev/mmcblk2. Give it your password, and you should be in fdisk. If you type M, you can see the available commands, and we'll go to expert mode later, which gives you more commands. P lets you view all of the partitions on that particular disk, and we just want to delete them all. So press D. It will ask you for a partition number. You can type any one you want. It will default to the last one. Since we're going to delete them all, I will just hit Enter to select 5. And I'm going to keep doing that until all of the partitions have been deleted. In this case, I'm on partition 2, and then this should be the last partition. So when I hit P again, you should see that there are no partitions on this drive. Now, keep in mind that nothing has been written to this drive yet. We need to type W to write these changes, but we're not going to do that yet. This allows us just to do things virtually so that we can set up everything before blowing away the data on this SD card. Take a look at the disk label type. In this case, my SD card is formatted with GPT, which is great. That's what we want to be. You might see something like DOS here. If you have master boot record, fdisk probably won't tell you MBR, but DOS really is MBR. You want to change this to GPT. So to do that, type G, and it will change the disk label type to GPT. So now we have a new layout format. Type P again, and if it wasn't already, you should see GPT printed here. Next, we're going to make a new partition with N. GPT allows us to have 128 different partitions, and you don't have to worry about primary versus extended anymore like you did with MBR. I'm going to just use the default of 1 for this partition number, and it's going to ask me where I should place the first sector. Depending on the type of media you're using, along with some of these other settings like your disk label type, the sector boundaries might change. I recommend trying to keep everything along sector boundaries just so it can find stuff a little more easily. I don't know if it's completely necessary. So for example, the sector boundaries for this SD card are every 2048 sectors. So I'm just gonna let fdisk choose where to put each of the partitions, even if it means I waste a little bit of space, which is just a few bytes or a few kilobytes here and there. For this first partition, I'm going to leave the default at 2048, so just press Enter. And then it asks me for the end sector. The other thing that I can do instead of defining an end sector is just give fdisk a size of that sector. I can do so with plus, and I'm going to say 256 capital K, lowercase I, capital B for kibibytes, or I guess this is kilobytes, but, 1024 bytes per instead of 1,000, so kibibytes. That will make the sector 256 kibibytes. So we print it again, and you see that indeed it is 256K. It gives me a start and end sector. It also defaults to a Linux file system, which could be ext3, ext4, something of that nature. We want to change that because our first stage bootloader cannot exist in that type of file system. So we're going to type T to change the partition, L to view all of the different partition types, and we want Microsoft Basic Data. This is something like FAT16 or FAT32. So we will Q to quit. And when it's asking us for the partition type, we will enter 11. That changes it to Microsoft Basic Data. We then want to repeat this process for the second first stage bootloader partition, the copy of that first stage bootloader partition. So N for new partition. We do want number 2. This is the second partition. Let it choose that boundary for us. So we'll let it default to 4096 sector boundary. And then once again, plus 256 KIB. That should give us a second partition. And we want to change the type again. So we want the second partition. We know it's going to be 11. And that gives us 2 sectors that we will use for the first stage bootloader. Next, we want another partition. It will be partition number 3. Let it choose the beginning sector boundary. This one is going to be 2 megabytes, or 2 mebibytes to be more specific. And we want to change the type to be Microsoft Basic Data again. So now we have the 2 partitions for the first stage bootloader, the copies of the first stage bootloader, and then another copy for the second stage bootloader. And remember, I'm getting all of this from that script that we looked at earlier and from information from the vendor presentation or the vendor documentation. We're going to make another partition. This will be partition number 4. Let it pick the starting sector for us. This one is going to be 64. This one will be 64 mebibytes, which will contain our boot file system. As you can see, it looks like it already contains an ext4 signature. I'm going to say yes to remove it. And if we print, you should see our partitions. Since partition number 4 defaulted to Linux file system, we're going to be copying over an ext4 image or file system to this anyway, so leave it at Linux file system. We don't need to change that partition type. We need one more partition for the root file system, so this will be partition number 5. Let it pick the default starting sector, and we're going to let this partition be the rest of the SD card. And if you notice, that should be the default. It will just go to the end. So we just hit enter. Yes to remove the ext4 signature if you're asked. Print it, and you should see the last 2 partitions are Linux file system types. We don't need to change those. And the root file system will be allowed the rest of that 8 gigabyte SD card. We need to make a few more changes here, but we have to do an expert mode. So hit X to go into expert mode. We can view the commands that are available to us in expert mode, and this allows us to do things like change the labels on the partition, set a legacy boot flag, which we're going to need to do. I'm going to type N to begin naming these partitions. I will start with partition 1. That is the first stage bootloader, copy number 1. And I'm going to type N again. We will do partition 2. This is first stage bootloader number 2. And I'm going to keep doing this. I did find that the second stage bootloader needs to be named FIP. I think, if I remember correctly, the first stage bootloader looks for a label named FIP in the partitions. So we will name it, this should be partition number 3, which we will name FIP. Keep going. Partition number 4. This should be boot or bootfs. Bootfs worked well enough for me. And then the final one is partition 5, which should be rootfs for the root file system. If you type P, you should see your partitions. You should see the starting and ending sector. You should see the type UUID and the partition UUID. And these are unique identifiers. The type UUID tells anything that's reading the partition table what type of partition it is. So these Microsoft Basic Data partitions should all have the same type UUID, but the partition UUID is unique among the partitions. So if anybody was looking for those or a particular partition, you can identify it with this ID number. And then finally, even though it's wrapped to a new line, you see the labels that we gave it. So first stage bootloader, FIP, bootfs, and rootfs. The next thing we want to do is type capital A to mark a partition as legacy BIOS bootable. I don't think we're using legacy BIOS here, but I could not get the bootfs partition to mount correctly without marking it as bootable. So we are going to choose number 4. Once again, type P, and you should see that this flag is now enabled on the bootfs partition. Hit R to return to the regular outside of expert command mode. Hit W to write to the SD card. This should automatically force a sync so that we don't need to enter the sync command in Linux. You can do an lsblk again to view the partitions, but as you can see, it's not much different from before because this is what I set up again. And now it's time to flash the image files that we want to these different partitions. To do that, head to our Yocto build folder, go to temp. Inside temp, you will find deploy. In there, you will see something called images, then the name of your board or platform or machine, more likely. And we want to go to that folder. This is where we have all of those available image files. And we want to look at that script to figure out exactly which images to use. So I will use a file browser to go into that same folder, which is deploy images, STM32MP1. The flash layout folder, we want trusted boot. And it was down at the bottom for me with the 157D-DK1 for the SD card. I will open that up again with an editor so you can see where I'm getting this information from. So the first two are this ARM trusted firmware for the DK1 board. And we're going to use the dd command to do a byte for byte copy to the partitions. The input file is in ARM trusted firmware. We want tf-a stm32mp157d-dk1-sd card.stm32. The output file should be dev wherever our SD card is mounted. And specifically, we want mmcblk2 partition 1. Type in my password and hopefully everything copied correctly. We want to repeat this command, however use partition 2 because that's the second copy of the first stage bootloader. So you see we have the 2 copies of that first stage bootloader. Next we want this FIP file. So we use dd again, FIP stm32mp157d-dk1 /trusted.bin, and the output file of that will be dev mmcblk2, and that's going to be partition 3. Then we want this boot file system, which should be in that top level directory of our machine images. Once again, we're using dd. The input file will be stimage-bootfs for Pokey stm32mp1.ext4, and we're going to be copying that to dev mmcblk2. to partition 4. And because things are starting to get a little bigger here, I recommend setting the block size to about 1 megabyte. That should make copying a little faster. This should take a few seconds, so wait a moment, and when that's done, we will do our final one, which for the root file system, which is this core image minimal.ext4 file. So we will enter that in, set our output file to be dev mmc blk to partition 5. And we will set our block size to be 1 megabyte again. That should set up the partitions and have the images for us. However, there is one little bug that I ran into, and it has to do with the fact that ST seems to want you to use their proprietary tool in order to flash a card. And if you're working with ST boards, I highly recommend using that tool because it automates this whole process for you. But I wanted to show you how to do it manually so that you learn what's going on when you create these bootable SD cards with embedded Linux for working with any number of single board computers or your own module for embedded Linux. The problem that I ran into is that the second stage bootloader does not know where to find the root file system. And we need to make one modification to a file to tell the second stage bootloader where to find it. To do that, we're going to need to mount boot file system, or the bootfs. When that second stage bootloader is running, it mounts this bootfs and it considers the SD card to be MMC0 in this case. It is no longer MMC2 like we were seeing on the host file system because this is the only flash storage that's available at the time. Note that on this board you do have other flash options available like eMMC or maybe some NAND, but for the SD card it's considering it MMC0. So this is where we need to go. And you're looking for this file called extlinux.conf. We want to modify that. However, I can't modify it with user privileges, so I'm going to have to do this with sudo. So I'm going to do sudo vi, or whatever editor you want. I'm going to go into not dev, but where it's mounted, which is media, my username, and it should be on bootfs. And you might have to call the mount command in order to mount it. I just decided to mount it using my graphical interface because it's easier and I'm lazy. In there we have mmc0.extlinux, and we want that extlinux.conf file. What you're looking for is this append line. You will see here that it tries to mount the root file system using a particular partition UUID. And that is one of the unique identifiers that we saw earlier when we were creating partitions. One option is to copy this partition UUID, go back into fdisk, and rename that partition UUID with this. That's because this is hard-coded by that tool that ST wants you to use to flash SD cards. But the other thing we can do is just tell this script, this configuration file, where to find the root file system using the partition number rather than a particular UUID, which you could also set here. You could copy the UUID of partition 5 and put it here, but since we know it's partition 5, let's just set it to open up partition 5. So I'm going to press I to insert, and I'm going to delete this entire section that sets that root variable. And instead, I'm going to tell it where to find partition 5. And I'm just going to tell it where that root file system is, which is at /dev/mmc_blk0, because that's what gets mounted in the second stage bootloader. And that's going to be partition 5. And I'm going to leave the other arguments alone. So save and exit that file. And unmount that partition. With that, we can remove the SD card from the host computer, and let's plug it into the board to see if it boots. Make sure that the boot 0 and boot 2 switches are set to on in order to boot from the SD card, and then plug in the SD card. I recommend attaching a USB cable to the ST-Link port first so that you can watch the boot process over the serial terminal. I won't give power to the board just yet. Let's connect our host computer to the serial output first. With our board ready to go but not powered on yet, I'm going to open a new tab in my console on my host machine. Let's zoom in here so you can see what I'm doing. I'm going to head back to the home directory so you can get a better view. I don't need to be in that output folder. And I'm going to run Picocom, give it a baud rate of 115/200. And we are going to connect to dev TTY ACM0. What I have discovered is that the ST-Link chip on this board will run with just a USB cable connected to it without having power being delivered to the rest of the board. This is very useful because it allows us to watch the serial output as the board boots. So at this point we're ready. I'm going to give power to the board, and hopefully we will see the first and second stage bootloaders coming alive and doing what they need to do. We should get to the point where it says starting kernel, and the kernel should be loading up. We've already been through the first stage bootloader, and the second stage bootloader fires off the kernel, and as the kernel boots, we should be inside of Linux with everything mounted. Hopefully everything went well, and you should be presented with a login prompt. Once again, the only user that should be available to us is root. And if you wait for a little bit, you might get some more kernel messages, so let those go by. Here we go. Here is the login prompt again. I will type root. There should be no password, and you have basic Linux. There should be really nothing here, just like we saw with build root. So let's look at our root folder. You can see all of the basic things here. And I'm curious if I have the df command. I do! So that is exciting. Something to note here is that I only have 1.8 megabytes available on my root file system, which means we will need a way to expand our root file system to take up the entirety of that partition that we made that was something like 7.2 gigabytes. So this is a basic running Linux operating system on our board. It just doesn't give us much to work with. Unfortunately, there is no easy way to expand this at the moment, as we don't have that nice script that comes with Raspberry Pi that automatically finds the available space on the root file system partition and expands the available space for us to fill up the rest of that partition. So for now, we will have to stop here and explore some of that later when we start diving into how do you develop things for embedded Linux. Next time, we'll look at developing applications for our custom Linux distribution. See you then.